All right. So I have the podium for an hour, I guess, or maybe 45 minutes. We'll see. I'll have lots of slides. I'm not going to spend my 45 minutes or 1 hour to refute Tony because I agree with most of what Tony said. So there won't be a historical supernova fight that you might see at some conferences, because I want to spend my time to talk to you about two important aspects of the problem that we'll get into in a moment. But first, I want to get a vote from you guys. I want to know something. I want to know what you think stabilizes neutron stars against gravity. And I want people to raise their hands. Okay, so I'm going to. There are three options, right? It's neutron degeneracy pressure. It's a mixture of neutron and proton degeneracy pressure, or it's none of the above. Okay, so who votes for A? Come on, raise your hands. Raise your hands. Raise your hands. Okay, all right. All right, B. Right? Who thinks it's neutrons and protons? Come on, you can't be so shy. There's no abstain option, right? So you got to raise your hands for something. Okay, C. All right, you guys are better trained than I thought. That's good.
Another category, which is all of the above. You can't really tease out
you can pretty much. You know the gamma very well. We'll get into this. All right, so what I'm going to be spending my time in the first lecture today is talk a little bit about core collapse, but not so much because Tony has covered that very well. But I'll talk about the nuclear equational state and about neutron star structure. And then I'll talk about numerical relativity and how we use general relativity to model core collapse supernovae, but also neutron star mergers. And then I'll talk a little bit about what we call the Iceon Toolkit, which is a set of open source tools that we'll use this afternoon to simulate the merger of two neutron stars. But first, let's go back to core collapse. Here's your evolved massive star. And it has this ion core here, about 10 to the 10 grams per cubic centimeter, temperature of half an MeV, an electron fraction of about 0.43 at the onset of collapse. And here you have a post-bound situation, very similar to what Tony showed. This is an entropy column map. We like to use entropy, specific entropy per baryon, because that has a nice dynamic range from here 1.5 to about 16. All the features that Tony spoke about. There's the shock, there's accretion, there's neutrinos cooling the interior, depositing some energy in the gain region. So there's a lot of different physics in here, right? There's gravity in there, there's the nuclear equational state in there, there's neutrino physics in there, there's neutrino transport in there, there's fluid dynamics in there. So there's this long laundry list of things we need to take care of. And if you count the fundamental forces in this problem, you get to 4. And these are the 4 fundamental forces that we know. So this is really a gigantic cosmic laboratory for fundamental physics. That's what a core collapse supernova really is. Now, neutron star mergers, and when I say neutron star mergers, I mean neutron star binaries and black hole and neutron star binaries. Neutron stars are typically 1.4 solar masses. A neutron star black hole binary may have a 1.4 solar mass neutron star, maybe a 7 to 10 times more massive black hole. So that's pretty uncertain because we don't actually know of any of such systems. We do know about 10 of these guys here. And they merge under the influence of gravitational waves. And I'll talk a lot more about these tomorrow. But I just wanted to show you that there's basically two possible outcomes. Here's scenario A. And this is a merger simulation done by Roland Haas, who's a postdoc at Caltech, part of the Simulating Extreme Spacetimes collaboration. So these are two neutron stars in the final phase. Here's the gravitational wave signal. We start the simulation something like 15 milliseconds before they merge. And in this particular case, why is my movie not playing? Here we go. You can see they're a little bit tidally deformed as they get close to each other because of the tidal forces they exert on each other. And the wave amplitude goes up, the orbital period goes down, the waves are emitted at twice the orbital period. And finally, they touch and they merge, give up a big burst of gravitational radiation, and they collapse to a black hole, and you end up with an accretion disk. Case B, same kind of general thing. There's one thing that's different, and I'll ask you guys what it is. You can start thinking. So they in spiral and touch and merge. But then what we have now is a hypermassive neutron star merger remnant that survives on a dynamical time. It may, over longer time scales, still collapse to a black hole, but not necessarily so. So what could be the two different things that could be different between case A and case B?
Softer crust and faster rotation.
Softer crust.
Well, it seems like there's more exchange.
Well, the fundamental qualitative difference is one collapses to a black hole, the other one doesn't, right? So that has nothing to do with the crust. There's no more crust when they touch because that kills the crust. So other opinions, ideas. Equation of state. One equation of state could be soft, the other one could be stiff. What other option do we have back there? There typically isn't sufficient ejecta to get rid of sufficient mass. It's all in the core.
Progenitor mass?
Right, just two different masses. And that's precisely what we did in these simulations. One had two 1.6 solar mass neutron stars, so the combined object had something north of 3.2 solar masses. And here we had a lower mass neutron star. So you have these variety of outcomes. If you have a black hole neutron star merger, your neutron star is actually being tidally disrupted by the black hole. The movie is a little older, so this is a precessing one. You can see the neutron star matter is disrupted. You get this tail of material that's being ejected. These accretion disks that are left behind after a merger or a disruption have dense, hot central regions. This is the neutrino luminosity, neutrino cooling from these regions. So even in the neutron star merger case, there's lots of neutrinos playing a role. These tidal tails can be very neutron rich. This is the electron fraction. So low electron fraction means matter is very neutron rich. So you have neutron rich ejecta, some of which are unbound, others will fall back. And you can do process nuclear synthesis calculations of that. And I'm not going to talk much about this, but I wanted to show this movie here that Jonas, who's sitting there, made. This is from one of these black hole neutron star merger simulations, where you end up with some neutron-rich material. And as this expands and moves out, it rapidly captures free neutrons. It moves up here towards the neutron-rich side. Eventually, the process freezes out. And then we have a decay chain that moves it back to the valley of stability. So there will be other talks here about the sites of astrophysical process. But neutron star mergers look like to be the favorite places. Now, if we now go back and think about what kind of physics did go into these neutron star merger simulation, and it's the same set of physics that goes into core collapse supernova simulations. It's gravity. GR needs to be included, otherwise you wouldn't get gravitational waves. The nuclear physics for the nuclear equation of state for the nuclear reactions, so that's the strong force. Neutrino physics, weak interaction. Fluid dynamics and magnetic fields. It could be magnetic field effects, so electromagnetic interaction. And of course, transport theory again, because you have neutrino transport that you need to solve in some way. So the takeaway of just this very phenomenological stuff that I just talked about is that core collapse supernovae and neutron star mergers involve the same rich physics. Both are cosmic laboratories for fundamental physics, and that's what motivates me to work on them. And they're multidimensional, or three-dimensional, fundamentally three-dimensional, multi-scale problems, because you don't just have to resolve the inner regions where you perhaps could do it with a simple computational model with a uniform grid or something. You need to resolve a big fraction of the star, or you need to resolve the ejecta from the tidal disruption and from the neutrino-driven winds that come from an accretion disk. So these are all very computational things. I'm not going to go into that anymore. I want to talk about some microphysics, and some of the microphysics may not be known by most people, or many people. All right, so here's your evolved massive star again, and you have the ion core. And when we think about the hydrostatics of the ion core, we think about just hydrostatics. So what provides the pressure? And really, this part is for the students. The senior faculty in the room should not try to answer these questions. What produces the pressure? We have ions, ion group nuclei, we have electrons, we may have some photons. So the total pressure is the sum of the partial pressure. The question is what dominates. Well, we can do some very basic estimates to figure this question out. Most of you maybe have seen that before. Just ideal gas for the ions. So they're Boltzmann gases. They're non-degenerate. Just have an ideal gas with some mean molecular weight down here. So you get a pressure, make an order of magnitude estimate. It's about 10 to the 26 dyne per centimeter squared. You go on and look at the photons. They're pretty simple, too. They just go with t to the 4th. So 4.6 times 10 to the 25. Now, the electrons are the ones that are really important. In the iron core, the density is 10 to the 10 times the density of water, so 10 to the 10 grams per cubic centimeter. So the electrons are relativistically degenerate. The degeneracy parameter, which is the electron chemical potential divided by kT, is much larger than 1, and the relativity parameter is much larger than 1. So in this case, you can take a limit of a Fermi gas, and you find that what we call a polytropic relation between pressure and density, where rho goes, density pressure goes with k times rho to the gamma. There's some constants, and it's about 10 to the 28. And gamma is 4/3 because you have relativistic gas. So if you compare all these pressures, and they're just restating these equations, you find that this is dominated by relativistic electrons. Okay, and that tells you why we actually get core collapse. And Tony might have mentioned this in his first lecture. Chandrasekhar proved that for a 4/3 gas, there's a maximum mass a pressure-supported fluid body can have that's being pulled by gravity, and that's the Chandrasekhar mass. It's about 1.4 solar masses. For symmetric matter, it goes down as YE goes smaller than 0.5. You can show, actually, this is a nice perturbation theory problem, that once this mass is reached, you go unstable. There's nothing to stop core collapse. And in an iron core, there's two ways to get there. One way is by just adding mass to the core, and the other way is by reducing YE. I'm sure Tony talked about that, and that goes through electron capture, so I won't go into more detail. There's one other important aspect that we need to know when we think about the equation of state during core collapse, and that's nuclear statistical equilibrium. And that's something that's very convenient. When we have high temperatures, by high temperatures I mean about above 0.5 MeV, so about 5 times 10 to the 9 Kelvin. The forward and backward reactions between nuclear transmutations go into equilibrium. They proceed so rapidly. So we reach chemical equilibrium where the sum for a given nucleus with Z protons and N neutrons, the chemical potentials go into balance with the individual with the neutrons and protons. We have two additional constraints. We have mass conservation and we have charge conservation. Using these constraints and knowledge about nuclear masses, we can derive a set of Saha-like equations, and I'm just stating this here, that give us the composition, the mole fractions, Yi, Ni over N, where these are number densities, for each nucleus, C and A, based on our knowledge of nuclear masses, which is in here, and the assumption of equilibrium. So we really don't need to track all these individual nuclei in our code if we have nuclear statistical equilibrium. The only variable we really need is the proton fraction, which is the electron fraction, really. It's the number of electrons per baryon, YE. So that's very important. It makes our problem much simpler. And we can now talk more about the equation of state by looking at a pressure density plot. So here's density in grams per cubic centimeter. And here's pressure. The absolute units don't matter. Don't worry about them. This is an adiabat. So we pick an entropy, 1.2 units of Boltzmann constant per baryon, and some fixed YE. So it's a straight line. And the slope of that straight line is just 4/3. It just shows us that the electrons dominate throughout collapse. We're collapsing all the way to nuclear density, which is above 10 to the 14 grams per cubic centimeters. And our DLNP, DLN-rho, which is gamma, is 4/3. It's beautiful. It's very easy to describe, but the electrons are not going to stop the collapse. because we've shown our iron core is unstable. But something happens over here, right, at higher density. Something happens. The slope of this curve changes. And we can actually plot the slope, which visualizes that much better. Where down here we are at 4/3 at low density, which is the electron gas. And as we get to nuclear density, which is about 0.16 particle per cubic Fermi, which is a nuclear unit, or 2.7 times 10 to the 14 grams per cubic centimeter, there's a phase transition. The equational state starts stiffening, becomes very stiff. Gamma gets large. When we look at what kind of particles we have around, at low densities, we have nucleons, alpha particles, and nuclei. Here we go from this inhomogeneous nuclear matter to bulk nuclear matter, which is pure nucleons. And the question now is, what is causing the stiffening of the equational state? Before we talk about this, the result of the stiffening of the equational state is obvious when we do a core collapse supernova simulation, for example. Here's time to core bounds. Here's the central density. You can see at core bounds, when we reach nuclear density, the collapse is stabilized. So if we didn't have that stiffening, if gamma wouldn't go up, if the pressure-density relationship didn't become stiffer or steeper, we wouldn't have neutron stars. Everything would just collapse into black holes, and that would be a problem. So the stiffening of the equational state leads to what we call core bounce. And the inner core, about 0.5 solar masses, will go back and bounce into the outer core. And then we get the shock wave, and then the other parts of the problem start. But let's talk a bit more about the stiffening here. And for that, we need to do some thermodynamics first. And I like thermal, so I'm going to treat you to some of it. So the first law says this: change in heat, the change in internal energy, PDV work, minus the change of particles in the system, mu I, the chemical potentials. They're basically the amount of energy you need to have to add a particle. In a non-degenerate classical gas, that's just the rest mass of the particle. I like to work in specific quantities, so I divide everything by the total number of particles and work in units of the number density. So I get something that looks like this. Now slightly rearranged for the internal energy. So the PDV term, TDS term, and then the chemical potential term. Here I was general. I said it depends on all the particles in the system, but really it doesn't because of nuclear statistical equilibrium. We can express in principle our internal energy as a function of number density, entropy, and electron fraction. Now I'm still not happy because my hydrocode actually likes something better. It likes different variables. It likes temperature instead of entropy. It likes number density, and it likes electron fraction. So I need to go to some other kind of thermodynamic quantity or thermodynamic potential. And I use the free energy for that, the Helmholtz free energy, which is defined as epsilon minus Ts. And the Helmholtz free energy has the additional nice feature that at fixed temperature, density, and composition, the Helmholtz free energy is minimized in equilibrium. And that helps us finding the equational state, because we might be able to write down some kind of expression for the internal energy or the free energy of our system. But we don't know if it's the true, if that's the true value, because there may be some degrees of freedom in there. However, if we know if the free energy is minimized, we can just look for this minimum of the free energy, and then we know we have found the true equational state. And that's usually done through a root finding algorithm, because we typically can't write down the free energy in a closed form, the solution for the free energy in a closed form. OK, so how do we get the equational state now from the free energy? Well, we look at its differential, and we use some algebra tricks. And then we look at derivatives of the free energy to get our various thermodynamic variables. So we take the derivative with respect to density at fixed temperature and YE, multiply n squared, and we have the pressure. That's how we get the pressure. We get the entropy, we get the chemical potentials. So finding the equational state boils down to finding the minimized free energy for a given density, temperature, and electron fraction. And this minimization also fixes the mass fractions of the constituent particles, so basically the equilibrium. The typical constituents in these nuclear equations of state are neutrons, protons, alpha particles, and some representative nucleus, AZ, or an ensemble of representative nuclei, depending on what kind of NSE composition one uses. Modern equations of state use thousands of these compositional variables. Of course, this is not the entire story. If the density goes very high, you might have exotic stuff like hyperons and kaons around. But in general, we'll write our free energy as the sum of partial free energies, which is convenient. We don't need to include the electrons in our free energy because they just add to it, and we don't need to include the photons. So we just here we just worry about the baryons. Okay. So let's this is it's all very nice, but it doesn't tell us really anything about the equation of state yet. So let's make a simplification. Say the temperature is 0, and we have a gas of pure neutrons and pure protons, which we might think might be appropriate for the interior of cold neutron stars. In some models, it is. This is a plot from Friedel and Weber. I should have given him credit here. So we were talking about this part of the plot where just neutrons, protons, and we can throw in electrons and so on. They don't hurt us, or muons. But there's lots of different models, of course, for nuclear matter in a neutron star. It could be strange condensates. There could be hyperons. There could be strange stars. There's actually some good observations that help us rule out some of the stuff, and I'll talk about this in a bit. But let's go back to the equation of state. Okay, so we can write down the equation of state for a pure neutron and proton gas. At 0 temperature, F is E minus Ts, so if the temperature is 0, F is E, or epsilon. So we just write down the energies of a Fermi gas of neutrons, add to it the energy of a Fermi gas of protons. This is, of course, depending on the neutron number density and the proton number density. We know the Fermi momentum. So we can plug in the Fermi momentum, which is this here. And this is just the Fermi energy here. We plug this in, and then we can compute our equation of state by taking derivatives. Right? We take the derivative of this expression with respect to density, and we get the pressure. If we plug this in, we find, depends on, gamma is 5/3 for this kind of equation of state. This is for non-relativistic neutrons and protons. So let's compare this to our previous plot and look at gamma in our simulation here. And we see, well, this is our line that we get from the neutrons and protons. And we see it's 5/3. It's not sufficiently stiff. It can't explain the stiffness here, this high gamma. And the upshot is that if we had a 0.7 solar mass neutron star, it could be supported by neutrons and proton degeneracy pressure alone. Anything more massive would not exist if there wasn't some additional physics that I haven't talked about yet. So neutron stars are generally not supported by the degeneracy pressure of neutrons and protons. Sure, the neutrons and protons are degenerate, but they don't support the neutron star. So we need to go a step further, and we need to think about what neutrons and protons do when they squeeze together a lot. And that has to do with the nucleon-nucleon interaction. So really, we have to have an interacting gas of neutrons and protons. And that's the simplest way of writing it. You have just the Fermi energies of the neutrons and protons. And then you have an interaction potential, the nucleon-nucleon potential. And that's where all the interesting nuclear physics comes in. So just to give you a little bit of a glimpse of this. So you have interactions between neutrons and protons. They're mediated by mesons. And there's pions. There's omegas, rho, and sigmas. Some of them have spin, others don't. The nuclear-nucleon interaction really is a many-body force. So it's not something that you could just write down QCD and get the nuclear interaction potential. It's something that comes out of a many-body calculation you have to do with QCD. And the important thing is that it's very separation dependent, it's spin dependent, and there's different kinds of interactions. There's scalar, vector, and tensor interactions. one that where we will find important is that the vector component of that interaction, which is mediated by the omega and by the rho to some extent, is repulsive. So if we take that into account, we can come up with a phenomenological model of the nucleon-nucleon interaction. We can do that by knowing that the nuclear force, the attractive part of the nuclear force must be short-ranged, because otherwise, we wouldn't be around. So there needs to be some cutoff, and we can model this cutoff by some e to the minus something, where these are scale factors that are given by basically by given the pion mass, which is the attractive part, and the omega mass, which is the repulsive part, and they just give us a scale. The scale is of a few Fermi, right? So just taking the masses. And these are Yukawa type potentials. So you have a 1 over r potential, and then you have this cutoff factor, which is, and you can see here there's an attractive part, which is the pi part, and a repulsive part, which is the omega part, just because of the sign in front of the term. So if you plot this, and I spent 2 hours trying to make a nice plot of this, finding the right scales and so on, but I managed to do it, you get sort of a, I didn't put a scale here, you get sort of a phenomenological description of the nuclear-nucleon potential, and you can see if you just think about it, you take derivatives of this potential to get a force, right? So you have a repulsive core, and unfortunately this was supposed to be blue, but it doesn't quite come out on that projector. You have the repulsive core starting here. You have a short-range attractive force, which is here because you're rolling down into the potential, and then you have your minimum. And that's where the nuclei live. So if it didn't have something that looked vaguely like this, maybe the fact constants may be different, there may be other terms. But if it didn't have this kind of phenomenological description, we wouldn't have nuclei. So we're pretty sure atomic nuclei exist, they're stable, they live down here in the minimum of the potential. Now try to poke, squeeze nucleons further together, and you'll hit the repulsive core, and that's what is really allowing us to have neutron stars. Otherwise, we just have black holes. OK, so this is the potential. What you now need to do to really write down the equation of state, you need to have some way of dealing with the quantum many-body problem. So you can do this by a brute force calculation. Just integrate. Use perhaps some approximation, like a Hartree-Fock approximation. You can make a mean field approximation. You can write down a Lagrangian for neutrons and protons in some mean field given by mesons. That will have some free parameters that you need to fix to reproduce laboratory results and perhaps neutron star observations. Or you can go yet a step more phenomenological. You use what was called the liquid drop model, and you just basically put in scale factors and parameters to match observations and experiments. So I want to talk a little more about the liquid drop model because it's so important. So in the liquid drop model, the masses of nuclei are just the masses of the constituents minus the binding energy, right? So the nucleus, because it's bound, always is lighter than the sum of its components. And then you parameterize this binding energy with various phenomenological terms, which are basically modeled after the idea of like a droplet of water. So you have some surface tension term, you have some Coulomb term because of the charges, you have symmetry because nuclear matter likes to be symmetric. So the more asymmetric it is, the more costly this term is. You have a pairing term because nucleons like to be paired in a certain way. And you have a volume term, which is just the nuclear force attraction. So all these numbers here come from trying to figure out ways to match the nuclear binding energy. So how do we get an equation of state, match the nuclear masses that are observed in laboratories? How do we get an equation of state out of that? Well, we actually don't take this right away. We take we make an expansion. We take we say, well, we sort of know what stuff happens at nuclear saturation density 0.16 per cubic Fermi, and we expand the binding energy, the energy per baryon. So we have this binding energy term here for bulk symmetric nuclear matter, and we expand it in density and in proton fraction, which is here x. So as you go away from symmetric matter, where there's as many neutrons and protons as protons, you get a symmetry energy term. You get a compression term here and a skewness term here. And again, we have these parameters that we tune from experiment. This is a measured value, the incompressibility, nuclear matter. Symmetry energy, we get constraints from experiments and from observations of neutron stars. And the skewness also is, I think, to some extent experimentally determined. So if we do this, we manage to do this expansion. What we then do, we write down from some kind of phenomenological nuclear force potential, we write down the energy of bulk nuclear matter, for example, using a Skyme potential, at 0 temperature, at saturation density, and then use, that will have some parameters because these nuclear force models have parameters. So we'll use our expansion, the parameters here, that needs to match at nuclear saturation density in symmetric matter. It needs to match our nuclear force potential, or vice versa. And then we can use the expansion to set the parameters of our nuclear force. And then in the next step, we need to generalize it. We need to have, this was for neutrons and protons, we need to include nuclei in some way. And we need to include alpha particles. And then we go about minimizing the free energy. We'll be finding the lowest energy state of our system of neutrons, protons, alpha particles, and some representative nuclei, or all representative nuclei that we're including. So that's how an equation of state is made, for example, the Latimer-Swesty equation of state that many of you who've done core collapse simulations have used. So this is the basic idea behind it. So let's talk about neutron star structure now and how we can perhaps constrain these equations of state. So in Newtonian, this is your neutron star structure equation. You'll find you can just make as massive neutron stars as you want, no maximum mass. Great. Eventually, you'll hit causality that your speed of sound will have to be greater than the speed of light. So, in GR, things look a little different. This is the Tolman-Oppenheimer-Volkoff equation, where you take into account that energy density actually also curves space. It's not just mass. And there's a pressure component as well that shows up in the stress energy tensor. You also have two different masses. That you have the gravitational mass, and you have the baryonic mass. So the gravitational mass will always be smaller than the baryonic mass because it includes the gravitational binding energy. And the radius becomes the circumferential radius. It's not anymore an isotropic radius. And this afternoon, I've prepared an exercise is to actually implement these equations, do a little bit of a computational thing, and compute neutron star structure. You basically integrate an ordinary differential equation, which this is a set of ODEs from r equals 0. At each step, we invert the pressure-density relationship to obtain the density. So if you do this for a range of equations of state, you get mass-radius plots. And this is a plot from Jim Latimer. Down here's radius. Here's mass of the neutron star. So you can see these are all different equations of state models. And they're all over the place. All over the place. So the only way we can really constrain this is by getting accurate. And again, these observations that I'll be talking about have systematics attached to them. But we can use observations to constrain these equations of state. And one way we can do this is by measuring masses. That gives us constraints on one of the axes here. We really want to have also radius, but just measuring mass, that's relatively easy to do. Astronomers know how to do that. Razier astronomers have gotten really good at that. You can use binary neutron stars and binaries. There's various kinds of binaries. And you get the mass function of a pulsar, where you know the total system mass, the companion mass, and then you get a mass estimate for the pulsar. So you need to have the companion mass, and you need to have the inclination of the orbit with respect to the line of sight to get the pulsar mass or the neutron star mass. The different kinds of binaries. The companion mass can be constrained via stellar models or perhaps relativistic effects. And inclination is the most difficult thing to measure. But in relativistic binaries, so for example, white dwarf neutron star binaries that are really close, the pulses are actually being bent in the gravity of the companion. So there's a Shapiro time delay, named after Erwin Shapiro at Harvard, who discovered this. So you get a delay of the pulses depending on the inclination of the orbit. And this allows extremely precise measurements very precise, much more precise than measurements we have for, let's say, ejecta masses of core-collapsed supernovae. You can get down, this is another one of these Latimer plots where these are all these different binaries. There's X-ray binaries, neutron star binaries, white dwarf neutron stars, and neutron stars main sequence binaries with various error bars. And in some cases, when we have relativistic binaries and we have the Shapiro delay, we can constrain neutron star masses to very, very high precision. And these are precision measurements. There's no statistical estimates of these errors. These are real measurement errors with all the systematics under control. So we do know there's almost two solar mass neutron stars, and that gives us a lower limit on the maximum mass of neutron stars. And we can go back on our plot and put it on. And that allows us to rule out all these guys down here, all the equations of state that do not support neutron stars, at least as massive as two solar masses. So that's good news, but we still don't have a constraint here. We don't know what the radius of the neutron star is, and there's all sorts of equations of state still allowing to have a two solar mass neutron star, but having very different radii. So how do we get the radii? Just to say, we don't have robust radius measurements at this point. There's huge systematics in all these measurements I'm going to talk about. Ideally, we want to measure the mass and the radius of the same neutron star, but that's going to be really tough. The main approaches to do that, and these are from Jim Latimer's review article, is observing the X-ray flux of quiescent and bursting neutron stars in galactic binaries. So these neutron stars accrete from a companion star, and once in a while they have an X-ray burst, and you can, by careful radiation transport modeling, you can infer the radius. It's very model dependent. LIGO, and I'll talk more about this tomorrow, will give us gravitation wave observations of merging neutron stars. In a neutron star merger, you get tidal deformation and post-merger oscillations in the merger, and in the neutron star black hole merger, you get a disruption of the neutron star and tidal deformation. That gives us a clue about the equation of state and the mass and the radius. And for a galactic core collapse supernova, the neutrino signal will tell us something about mass and radius of the protoneutron star and about the stiffness of the equation of state. So putting observations together, Steiner and Latimer have made these plots here, where here's radius and mass, and these are now Bayesian statistic constraints, taking all the observations, putting them in, throwing them in, putting some priors in. And they say the radii should be along this range here. The mass and radii should be along this range. If you take that range, which is pretty narrow, between something like 12 and 14 kilometers for the bulk of the neutron stars, right? You get a pressure-density relationship. You can basically infer the equation of state from these mass and radius estimates. But it doesn't fix the model dependence. But if we took this stuff at face value, which we shouldn't, it's just an example of what one could do if one had the constraints, the model dependence under control. One could put a constraint also on the radius, which would rule out these equations of state with the very large radii at large masses and leave these guys here. Now, this is just a subset of possible equations of state. There's actually these are all cold equations of state. I didn't put in any of the supernova equations of state that we use in our core collapse supernova models, because here we're talking about cold neutron stars. If you're interested in more stuff about the equation of state, I put together a little literature list. I'm not going to go through this. The slides are going to be online, I presume. So you can just go and read up on these things. In particular, the basics of the equation of state that I talked about are in these two books. And there's more supernova-related stuff in here. But now I get to the second part of my talk, and I'm almost running into my question time, but I really need to go through this because you'll be using the Einstein Toolkit this afternoon to model the merger of two neutron stars. So for that we need to have numerical relativity. So GR is a geometric theory of gravity. You've all seen these space-time curvature diagrams. These are the Einstein equations. Look pretty abstract and neat. They're a mess. If you look at the left side, you have the Einstein tensor, which describes the geometry of space-time, or what we call the curvature of space-time. On the right-hand side, you have the stress-energy tensor, which sources curvature of space-time. These tensors are all symmetric. In 4D, you have 10 independent tensor components that you need to deal with. You introduce a metric. Metric is the most fundamental quantity in GR. We use it to measure physical distances in curved space-time. We can derive any curvature from the metric. And this is a line element for some line element here, some distance in space-time. And note that here and throughout this talk, I'll be using Einstein sum conventions, so indices that appear twice imply a sum. Partial derivatives that we're used to from our Newtonian physics are actually very coordinate dependent, so we don't like them. We're going to have to use covariant derivatives that are coordinate independent, where we have a partial derivative, and these are just some notation here. We either use d beta or semicolon beta. We have a partial derivative, and then we correct for the coordinate system we're in by what we call Christoffel symbols that contain first derivatives of the metric. And any physical meaningful theory must, of course, be coordinate independent. So the laws of physics, corollary to this is that the laws of physics hold in any coordinate system. So this alone doesn't tell us yet how we solve the problem of two merging neutron stars. We need to go a step further, and we need to actually take our 4D space-time and put it into a form that we can actually solve it on a computer. And what we do, we slice it up. We say, well, let's take the spatial coordinates and separate out a time coordinate. And here are all the spatial surfaces, or hypersurfaces in space-time. They're three-dimensional. Also here they're two-dimensional. And we connect all these hypersurfaces. These are all space-like, so individual points can't be reached. They can only be reached as the time goes forward. We connect these with unit normals that describe the time direction. Then we can also change the coordinates from one time slice to the next with what we call the shift vector. And if we use this split, this 3+1 decomposition, and apply it to the Einstein equations, we end up with 12 first-order hyperbolic evolution equations, so stuff that has a ddt in front of it. We just integrate it in time. We get 4 elliptic constraint equations that we don't evolve in time. We just use them to check for the quality of our simulation, and we use them to construct the initial space-time. And we have coordinate degrees of freedom that we introduce by making the slicing, the lapse function alpha that tells us how big the step is in time that we're taking from one slice to the next. And the shift vector beta, which has 3 components, is how the coordinates change from one slice to the next. So if we do that, we get a bunch of more quantities. So the split, we pay the price for the split by getting more variables. We have the 4 metric, we have the 3 metric, we have the lapse function, the shift vector, various quantities that will pop up on the next slides. This is how the 4 metric is constructed out of the shift and the lapse and the 3 metric. And we get another quantity, the time derivative of the metric, which is called the extrinsic curvature, Kij. And that has, so Kij will be the time derivative of the metric and some coordinate-dependent terms coming from the shift vector of how the coordinates change from one slice to the next. We have a 4 velocity, and we make a 3 velocity out of our 4 velocity, which is defined like this. And we have the common Lorentz factor, which we call W here, to not confuse it with any gammas. So if we do all of this, we get a set of equations, the Arnowitz-Dieser-Misner equations, or in the formulation by Jimmy York. So here's the time derivative of the metric, which just involves the extrinsic curvature. And then we have a second derivative, equation, the time derivative of the extrinsic curvature. And that's a big mess. All over here, these are just definitions so that you know what goes into them. And we have the constraint equations, the Hamiltonian constraint, which is an energy constraint, and a momentum constraint, which is vectorial. And here is the source. This comes from the stress energy tensor. And here's the momentum source. Here's the energy source. All right, so great. We just put this in a computer and we simulate, right? Doesn't work that way. First of all, we haven't said anything about the gauge yet. We haven't said what we're going to do with lapse and shift. In analytic relativity, anything goes, because this is a gauge, right? Gauge quantities can be chosen to be anything we want. Problem is, the gauge controls our coordinates. And what GR dynamics will do, and here you see some kind of black hole with a jet or something is twisting space-time. It twists space-time, so the coordinates are being twisted, and we can get singularities that are not even physical singularities, coordinate singularities. And we can get physical singularities too. A star might collapse to a black hole as a singularity. So for numerically stable evolution, we must avoid these singularities somehow, and we need to control the distortion of the coordinates. There's a particular gauge that's called minimal distortion, for example, that tries to use the shift vector to counteract the twisting of the coordinate lines. So we need to do that. But then we do this, and we think it's all great. And then it turns out that numerics bites us. The ADM form of the equations is unstable. We can actually numerically, analytically prove that it's an ill-posed system of equations. Small errors in the constraint equations that are not being solved, that don't go into the numerical evolution, they get amplified over time, and that amplification can become exponential, and then your entire evolution scheme breaks down. So we can't use these, they're not exactly neat, but we can write them down easily. Equations, we need to do something else, and this is what took numerical relativity, this field, about 30 years to figure out. One needs to use different, and this was mainly done by trial and error, different formulations, because what you can do, right, because these constraint equations have zeros on this side, you can arbitrarily add parts of these constraints to these evolution equations and change the nature of the evolution system by just having more terms in there. They could damp out oscillations. They could damp out constraint violations. And so the field did this. And in the early 2000s, we came up with a set of different evolution systems that I won't talk more about. I'll give references at the end of the lecture that you can go and read more about. These equations are typically solved by just doing finite differences, high-order finite differences, fourth order, sixth order, eighth order, or spectral methods for discretization. So if you think about a numerical relativity simulation, it looks like this. You start out with initial data that satisfies the constraints equation. So you have a solution of the Einstein equations, and then you integrate in time. So you evolve one time step, and each time step you evaluate the right-hand side of your equations. That means right-hand side of the curvature equations, the gauge equations, how the gauge evolves, hydrodynamics and radiation, which I haven't talked about yet. And then you apply the update, and you do, at each intermediate step, sort of a first-order, forward. This is a very simplified thing. In what you really do, you end up with a high-order Horanga-Kutta integrator. So typically uses a fourth-order RK4. And then you have analysis and output, and then you go and take the next time step. What I didn't put in here is what one frequently needs to use, and that's adaptive mesh refinement, because if you have matter that you need to finally resolve for the hydrodynamics, but you also need to cover the large scale of the problem. Okay, hydro. We haven't talked about, so far we talked only about the curvature part. Now the source of curvature, we have a mass flux and we have a stress energy flux. And we have conservation equations for these, just very similar to the Newtonian conservation equations. And we end up with a formulation that's called Flux Conservative, where we have some state variables and time change of the state variables, some fluxes, and some source terms. And this is a mess. You can look at it later. You end up with a set of conserved quantities, a generalized density, a generalized momentum, a generalized energy quantity. You have flux terms for these guys, and you have source terms. The source terms are what in your Newtonian hydro would be the gravity source term that would be an acceleration term. And this is what these terms are. There's a complication here, though, and you can see that right now. We evolved these equations in our hydrodynamics code, but they're not the primitive fundamental equations of our equational state. They're generalized equations. So at each time step, actually at each time integration substep, we need to go back from the conserved equations to the primitive equations to be able to evaluate our equational state or do coupling to neutrino transport or something like that. So a consequence is that we need to do that. There's no closed form expression of this procedure, so one needs to do a root finding at each time step, at each time integration substep for each numerical zone. And this makes the general relativistic hydro a lot more expensive than the Newtonian hydro. So I'm going to skip the next slide. I'm going to talk about the Iceon Toolkit briefly before I stop. And it's a project that I've been involved in for a number of years. There's been 2 papers describing this set of codes. It's an open source software, a set of software components for the simulation and analysis of general relativistic astrophysical systems. And the basic motivation of this is that if it can't be reproduced, it ain't science. So if I keep my code closed, and I invested 20 years in my code, then I'm proud of my code, but perhaps no one else will ever be able to reproduce this because they don't have 20 years. So the idea is here, we make our stuff open, available, and reproducible by others. This is supported by the National Science Foundation. We're a collaborative grant, and the current set of collaborating institutions are Georgia Tech, LSU, Rochester Institute of Technology, and Caltech. We have about 110 users, 53 different groups, about 10 active maintainers. I'm not sure if I count myself in here because, unfortunately, I don't get to write much code these days. The goals is reproducibility. It's to build a community code base for numerical relativity and computational relativistic astrophysics. It's to enable new science by lowering the technological hurdle to avoid people having to reinvent the wheel, write another Einstein solver. That's a big mess. You don't want to waste your 5 years of grad student time on this. You want to do astrophysics. It enables code verification and validation because there's an open code base. You can just go look what the code does. It allows for physics benchmarking, and we have a set of standardized tests that each new revision of the code has to satisfy, so we enable regression testing. It's also meant to enable users who may not be so computationally skilled to use some of the new technologies in computational science and new computer hardware like GPUs and so on. And it also comes with a set of cyber infrastructure tools that allow you to manage code and data. There are regular releases of the toolkit. The most recent one is the Wheeler release from May 2014. You can get support on the Iceon Toolkit via a mailing list, and we have weekly open conference calls that you can just join. We have working examples for black hole mergers, neutron star mergers, oscillating isolated neutron stars, and magnetized core collapse to a neutron star. Here's just a list of available components. This all builds on what's called the Cactus framework, which is a modular framework where you have a flash and then you plug in physics modules as thorns into the Cactus flash. It has an adaptive mesh refinement driver, has a hydrosolver, it has various space-time solvers that implement various different evolution systems, has initial data solvers and can import initial data from other codes. There's lots of analysis tools, and visualization is done via the Visit visualization software, which is also open source. Just a few cool components that I like about the toolkit that are sort of more computational science tools. One thing is called Get Components that will allow you to pull in software components from globally distributed version control repositories or websites. SimFactory is something that makes your life easy, and you'll be using it this afternoon. If you get a new want to run on a new computer, you get SimFactory, will automatically configure it on that computer and build the Iceon Toolkit, and will allow you to manage your simulations. You won't be editing parameter files by hand because that introduces human error. And something that's really cool is what we call Formalin, and that's a code provenance tool in computational science parlance. And basically what it does, it takes a snapshot of the full code that you use to build your executable and embeds that code into the executable. So whenever you run it, it will write out a full tarball of your source code and into your output directory. So if in 2 years from now you pull that from tape and you don't know what code produces that, you actually have the code with the data. And that has saved my behind a few times, I have to say, over the past decade. OK, so the workshop this afternoon will be doing neutron star mergers. You'll be able to do multiple of these exercises. You should, if you want to do the neutron star merger, you need to start with this, because in order to see anything, you need to run for at least 2 hours. We'll solve the TOV equation. That's more of a actual coding exercise. I have a code skeleton that you get to use. And a more of a code running exercise is to use our open source GR1D code, which is a stellar collapse code, to study circularly symmetric core collapse to neutron stars and also black holes. So GR1D can dynamically form black holes. So with this, I close and just leave up, well, two things. First, the literature list. You can just go and look at these. This will be on the web, so you don't have to write anything down. But very importantly, and there's many students in this room, and that's really important, if you're not yet a member of the APS topical group in gravitation, we really need you. We need you guys to go to APS, the American Physical Society, and sign up for GGR, because next year is the centennial of general relativity, and we want to reach division status by 2015. That means we have to have more than 1,500 people in our topical group. And I think grad students get a number of these topical group memberships for free. So the hurdle for you guys to join if you're not yet a member is really low. So I encourage you to do that. Thank you.
Questions?
You mentioned a neutrino emission from the mergers. How is it comparable to the core collapse signal?
It's very comparable in terms of total luminosity. The matter composition is quite different. It's more neutron rich, so you'll have a different balance of the fluxes. But of course, it's not going to be observable because the galactic merger rate is 1 in a million years. And then you need to go really far out to have a frequent merger rate, and we won't see neutrinos at 100 megaparsecs from Earth. Oh, same energies. Same scale of energies. Tens of MeV.
I would add that you're right. I mean, the expected emergent energy spectra and fluxes should be different because these are very neutron-rich objects.
Right.
And so the real issue is, in my mind, is whether the neutrino interactions can reset the electron fraction of the ejecta.
To some extent, they can.
And
if you wait,
how rapidly things outflow, which as you just pointed out, is kind of an objective of the hydro calculations, the GR calculations, and that's a tough one.
Yeah. If the stuff hangs around for long enough, it gets protonized.
No, because a lot of the neutrino emission will probably be thermal.
Uh,
In Nui and Nui bar pairs, that's typically what happens. Although there will be more of an excess of Nui bar.
As if the hypermassive neutron star runs around, stays around for sufficiently long, you end up actually having more.
I think we're saying the same thing.
reprotonize.
So if you have roughly equal numbers of Nuis and Nui bars, then you're going to wind up.
Sure, but
ultimately
you won't be
proton,
changing it.
A slight excess of protons
Okay.
over neutrons,
Right.
which of course is a disaster.
Well, I mean, that's we want to have our process somewhere, right?
Question: how do you define the mass of a neutron star and the radius of a neutron star? I mean, for the Earth, it's very simple. I mean, the solid Earth, air, I see the transition, that's the radius of the Earth, and then within the radius, that's the mass. A neutron star, I think about it, if you draw a curve of mass enclosed within a certain radius. I imagine that near what you call the surface of a neutron star, there will be a sharp curve which is dropping like a...
Yeah, so the radius is the more difficult problem. So the mass is, we can measure the mass, we measure the gravitational mass.
I know,
So we can do that. That's a strong equivalence.
The real thing is that how do you
Yeah,
define the
so
radius?
that's a real problem. That's why these radius measurements that are based on estimates of where the surface is are so bogged down by the systematics, because it's very hard to define that surface very well.
You see that it's
Yeah.
cut off.
Absolutely.
All right.
Yeah.
Questions? Alex. Loud, Alex, because some of us are hearing impaired.
The instabilities that you mentioned in the GR slide, are these basically gauge degrees of freedom that get unstable, or how should I think of them?
No, the gauge is stable. But basically, right, you're making a discretization error at every time step. Let's see. Here we go. So these equations are valid for a solution of the Einstein equations, right? You measure how close.
The reason why I'm a little confused is because you say I have the gauge degree of the gauge constraint somehow, and the goes away. So that's why.
What goes away?
You said that if you take your gauge constraints, you add them to the equations with appropriate coefficients, the instabilities become.
No, that's not true for this system. There's two sets of instabilities. One is ill-posed coordinates, where you just can't numerically, with the resolution that you have available, you can't resolve it anymore. That's a problem that any evolution system has. So if you have a pathological gauge, you will always have that problem, no matter how you formulate your equations. What this evolution system has is that if you have a little perturbation about your solution of the Einstein equations, whose quality you measure with the Hamiltonian momentum constraint, then the property of this evolution system is to amplify the perturbation that you have. So you get an instability that's amplified by the structure of the equations. In some sense, these are not conservation equations, but if you think about it, if you were to think about it in the context of the hydro equations that are conservation laws, but they allow weak solutions where the integral form of the conservation law is satisfied, but the differential form isn't satisfied anymore, and you get oscillations. This is a similar but not the same kind of concept. The structure of the equation admits the development of numerical instability. So you want to find a structure, a reformulation of the equations that doesn't do that. And that was done over 30 years with trial and error.
I'm just trying to understand, there are physical degrees of freedom which are unstable because of discretization?
Because of the structure of the equations. So there's, we're talking, this is applied math really, right? So in applied math, when you have a hyperbolic evolution system, you can have different degrees of hyperbolicity, right? You can be hyperbolic, you can be symmetric hyperbolic, you can be strong hyperbolic, and so on. And there's different ways of writing out the equations that have different properties in the space of these hyperbolic evolution systems. And this is a poor formulation, whereas there is this generalized harmonic system, for example, that's a reformulation in terms of wave equations, and that can be shown to be strongly and symmetrically hyperbolic and is manifestly stable. However, not for poor gauge choices. If you're trying to solve this on a set of coordinates that are just ill-posed, even that system will blow up. I see you're not satisfied. I can point you to some.
I don't know what this means, right? Because in gauge theories, of course, there are artifacts that
Yeah, but these are artifacts that only show up when you discretize them and try to solve them.
Here you say that if I go on the Newtonian limit, then I don't see them. So it's the addition of what? High derivatives?
Well, these are highly nonlinear, right? GR is a nonlinear theory, right? So here it's all nonlinear terms, right? And that's the problem, yes.